All right. So this is what we have, what we had last week and today. So for the application of the integral, we skip a few things, just make things clear. So we have, oh, sorry. Okay. So area, we covered that. Volume of solids, slabs, discs, washers. Okay. Solids of revolutions, shells. Okay. And then we skip this one, like a plane curve. Okay. And then 5.5, section 5.5. One. Okay. Center moment and center of mass. Okay, we did that. And we skip this one. So, okay. Only those, let's see how many, 5 sections from this chapter. Right. So let's continue with the next chapter, which is about transcendence functions. Let's see, this is the, say, okay, so we're talking about, I'll show you first the, okay, so this transcendental functions. What is transcendental functions? Transcendental means not algebraic. So what's algebraic? Algebraic is something that you can get from polynomial by using additions, subtractions, multiplications. So those also rational functions, or those are algebraic functions. Okay. And something's not algebraic called transcendental. So the first transcendental that we know is the trigonometric functions. Okay. And the next is what we have in this chapter. Okay. So let's see. Is there anything that we will skip? No, we will cover this. Uh, all of these except this. Okay, we'll have those all. Okay, so let's start with the first one about the natural log functions. So let me just write down what I mentioned earlier. So first, what we call algebraic functions. Any functions that can be polynomial using arithmetic operations. So that is plus minus. Okay. So example of this is was polynomial itself, rational functions. Okay. And oh yeah, roots. So roots of polynomial or and root of rational functions. Okay, so this is algebraic. So something's uh, not algebraic. We call it, it's called transcendental. Transcendental. Okay, so the easiest example of transcendental functions that we know is the trig functions. Okay, trig functions, and then something that we discussed in this chapter. Okay, so let's start with the what we call a natural log functions. Okay, so this is the idea. Uh, you know that the antiderivative formula, so the definite integral, sorry, indefinite integral of x to the r, okay, dx. Remember the formula for this? Okay, so you raise the power by 1, okay, and then divide the result by the new power, okay, plus c, of course, okay, constant. And the thing here, because, let's see, because you have division by r plus 1, so it imposes a conditions that r plus 1 cannot be 0. So it is r cannot be negative 1. Okay. So the question, natural question would be, what happened if r equals negative 1? Okay. So this is something that we haven't discussed up to this point yet. Okay. All right. So let's see. This is the idea. Okay. Okay. For r minus 1, so f of x would be 1 over x, right? Okay, so let's see let's picture this one. Let's picture this one. Let's picture this one, especially for x, say positive. Okay, so for x positive, the picture looks like this one. It is symmetric. This is x. This is y over 1 over x. Okay, so if we have this one, um, find example from 1 to, say, to 5, 1 over x dx. Here you cannot do this one by using the fundamental theorem of calculus, FTC2 cannot solve this. Why? Because so far we don't have antiderivative. Sorry, not to say antiderivative, say explicit antiderivative of 1 over x. Okay, so you cannot say that it is difference between something, say the capital F at 5 and capital F at 1. Okay? But if you do this one, let's do interpret this integral. It is, you see, this is area under the curve 1 over x between x equals 1 to 5. Okay, so this is area under the curve x. Okay, and let's see, let's take this one. And it turns out that it is clear that 1, 2, 3, 4, 5. That's the area. Good. So what we have so far is this area here. Right. So you see, this area exists. It's there. So you should be able to compute the area. The region exists. Right? Area. Sorry, this is area of region. This is the region. Says, therefore, the area should be able to determine. You can use approximations, whatever. Okay, so in fact, this integral exists. Or x as area. Okay. So that's why all right, so let's just make up these functions. Right? So let's define. This is e for x. Say this is x. Say positive. So these functions for x greater than 1, obviously 1, it should be f of x is the area of the region. There we go. All right. So there's a new functions. Okay, so let's see what's happening to the properties. So properties of f. Okay. First is, well, uh, so f of x is, you see, because this is area, this is positive if x is larger than 1, right? This equals 0 if x equals 1, right? For x bigger than 1, so meaning to the right of 1, this area is, you see this area, so it must have a, sorry, you see the region, it must have a positive area. Okay. For x equals 1, so coincide with 1, so there is no area, there is no regions, just line, so the area is 0. Okay, so when x there, that should be negative. Why? Because you compute the other way around, right? So the properties of integral. Okay, so this is one property. Okay, and let's see, what else? Oh, we know the derivative. Uh, so f of x t. So it doesn't matter. You can use t or r or s or whatever. So it is name of variable, as long as it's not x, because we use x as the variable here. Okay. So is antiderivative of 1 over x. Why? Because if you take the derivative, right, so ddx of t by fundamental theorem of calculus, the first one, you see that uh, the lower bound is constant 1, the upper bound is the variable itself. So when you take derivative of these integrals, derivative and integral cancel, leaving you is just replacing t by x. Right? So it is the antiderivative. So we have an explicit antiderivative. Right? So this f. Okay, let's do something else. Um, let's see, what if ax 1 to a, okay, so let's see. Sorry, this is what I meant. If you take the derivative of ax, right, so you get, see, this is by chain rule, right, times derivative of this ax is just a. Okay, and derivative of this is just, let's see, here. So 1 over x times a, so just 1 over x. Okay. Okay, so let's see here. So the first process, if you take derivative of this is antiderivative, 1 over x. If you take f of ax is also, you end up with 1 over x. So here 1 over x has two antiderivative. Has course, more than two actually. X and f of a x. Okay. And recall, if you have more than one one antiderivative, what happened? How the two antiderivative relates? What happened if you have two antiderivative? What do you know about the about those two? How those two are related? Anyone? How the antiderivatives of functions are related? Are they going to be very different or what? Or similar?
Is the antiderivative it's only unique up to a certain constant.
Constant. So the difference of these two are constant. So this one is just a the first one plus some constant. Okay, because if there are two antiderivative, then x minus x equals constant. C constant. Right. Okay. Let's try to plug in x equals 1. Okay. So you see what you get is f of 1, right? F of 1 here, which is, we know f of 1 is 0 because of this. Okay? Because the area between 1 and 1, so that's must be 0. Okay, so what you have is f of a is equals, let's see, is that f of ax equals, so I move this x and then plus c. C is this f1. Sorry, fa. Let's see, f of ax, or become plus. Okay. So a can be any positive number. Okay. I won't derive this, but it is similar here. The fourth one is this. It turns out that if I have something like this, then it is f of a minus f of b. Okay. And then the last one is f of, say, a to the r. That is r f of a. Use the same trick using derivative. Okay. All right. Do you remember what the properties 3, 4, and 5? Okay. Remember that the log A plus, oh, sorry, log AB is log A plus log B, for example. A over B is just log A minus log B, and then log of A to the power of R is this. You can take the R, factor the R out. Okay, so like this. And of course, you have also log 1 is 0. Okay. So in fact, this is true for any base. Any base. This is base 10, right? Log base 10 for any base. So we usually write something like this. Some prefer right here, base A, or base A. Okay, so log functions. All right, so you see that the f here, let's see here, f1 is 0, f bigger than 1 is positive, okay. It is a negative. So you have this property also, 3, property 3, property 5, this log, property 4, property 5. Okay, so f has these properties. So that's the reason why and f is log functions. But the thing is, we don't know the base is. So I just say with some base A. Right? So now the next question would be A equals what? Okay. All right. Later uh, we will try to recover this A here. It turns out that A is the number E, 2.71 something, right? And we'll see, use some numerics, how to get this 2.71. Okay. Right, so, and F, because of this, we don't know yet the log functions. F is called natural log functions and denoted by Ln of x, log natural of x. Okay, so those are the properties of a log natural. Okay, this. Okay, so to summarize, before we get into some examples, nice. Now we can compute this one here. Should say, okay, it's the R x. This gave you this one. See if r is not equal to -1. When it's the -1, so you get ln. Okay, and with those properties. Right, so let's do some more examples. So let's do this one. The x of log ln of x. Okay. Okay, first derivative. Okay. The x of ln of x. Okay. So this is what you have. Okay. This is antiderivative of ln of x is antiderivative of this. So second example, what if something that looks like this? Oh, -x. So you just use chain rule. Okay, so 1/x times -1. So it is also x, right? So it says that antiderivative of now is the same, not only 1/a ln of x, but there. So these are the first thing that you should recall. Okay, so let's see. There's another example. What if ln of say x squared plus x plus 5, for example? It looks like this. All right, so this is 1 over in rule. You gotta multiply a derivative of this. So x plus. Yeah. Okay. All right. What about this one now? We use this integral formula. Dx over x plus 1. Okay, using substitutions. Equals x plus 1, u equals dx. So this becomes integral of du over u. So this is ln of u. Ln of x plus 1. Okay. And basically what you have here, oops, I have only a few minutes ago. Let's see here. This is x dx. This is x squared. Yes, just x squared plus 5, for example. All right. So this is also substitutions. If you use substitutions, u equals x squared plus 5, then du would be 2x dx. So this first, we have this just x, just 2x. So we have this x is 1/2 of the du. All right, so with substitutions, what we have is, so this is 1/2 of du, so x dx compared to 2x dx. Again, this gives you ln. Let's put it back. And of x plus 1. Okay. See, it's the same thing if you have a, now we can compute integral of tangent. Right? Why? Because tangent is sine x over cosine x dx. Again, using substitutions, u equals cosine. So u is cosine negative sine dx. So exactly what we have here, sine. Okay, except you have this negative sign there. So if you substitute, you get this negative. This is du. This is u. And you get negative ln of what? That's equals to negative ln u is cosine. Okay, so we have those kind of tricks. Okay, one more example is what we call find the derivative of, say, something that looks like, it's not difficult, but nasty, I would say. X squared plus 5, 1/3, x plus 7 over, say, this is square root of, no, just multiplications. There, so something that looks like this. Okay, so you know the rule how to compute this integral. You have to do quotient rules, right? And inside the quotient rules, you have product rule because this is product. Numerator is a product, and the denominator is a product also. Okay, let's make it more nastier by putting there 7/3. Right. So it's not difficult, but complicated. So the idea is, let's compute the ln first. Okay. First apply ln. So when you apply ln to this one, okay, what you have is, okay, recall, this is a product. This is a power. This is a of 1 over division. Okay, so you can use these properties of the if the of logarithm. We call these properties. Sorry. If they have product, when then you have a sum. You have a division, then you have a difference. Okay, when you have power, you can take the power out. Keep log. Okay, so using this, when you apply log to this one, you actually have, all right, so this is this plus this. Take the 1/3 out. Sorry. Ln of x squared plus 5. Okay, and add ln of x plus 7, because this is the, in the denominator you subtract. and you have 1/2 because that's square root. Another subtraction. Sorry, miss the ln. ln ln of there. Okay. So now you don't have a product or quotient here. Okay, so it's easier to compute the derivative here. Okay, let's see. So let me just log diff. Yeah, this one. So let's take the derivative. See, this is f of x. Okay. Here, this is log of. Okay, so let's now take the derivative. So d dx of f of x is d dx of, so not equal, sorry. We are not computing that one. What we compute here is d dx of ln of f of x. Okay. So by the formula ln, the derivatives in chain rule, this is 1 over f of x, right, times derivative of that. Okay, and let's see, derivative of this is hold on. I suddenly forget. Okay. Mm, this is the last one. Let me just take. So left hand side, right hand side, take d dx. Okay, same thing here. So the left hand side you get 1 over f of x, f prime of x. Okay, and then you take d dx of this. That's easy. So 1/3. This is just x squared plus 5. This is x. Okay, this is plus ln of, sorry, derivative of this. Yes. Okay. Derivative of this, x squared plus 3 times the derivative of x squared, x, and minus 7/3 ln of this. Oh, it's this. Okay. Multiply by derivative of this, 2x plus 7. Okay, so you get now the f. Let's see, 1 times f of x. whether to write this down. Okay, this kind of trick is called log diff, logarithmic differentiations. Okay. All right, I'll stop here and let Kemal take over for the problem sessions. Okay, stop it.